structure of the planet, how can we assume the degree of the desired model or the difference, the excess?
We have to have the prior knowledge of the planet, either as an assumption. We have to.
Okay.
We cannot start without having the prior knowledge. We assume that it's second order, first order, whatever it is.
Even if the diagram there is assumption model, when you see like the diagram for it, there something like assumption.
Assuming the
yes, assuming.
Yes, you have to.
So you mean that first, for example, there's some modeling or first identification?
Modeling will just see the way the system responds to certain functions. على طول you can you can have some approximated one. It does not mean that you are going. It could be that you don't get it from the first time. You need to read it. And you did it, and then you try to do the control. They are not matching each other, so there's a problem in modeling. Today we are going to go one step further. We are going to what we did last time for the MIT rule. We worked with the feed forward. So it's only just a game that we have used in order to design the controller. And this is the structure that we got last time about this. We have noticed, this is one thing that is very important. When we change the input, we change the way the system is responding. Even when we went to second order system for both still feed forward, we were able to have the system completely unstable, right? You remember that, huh?
Yes.
But what we did last time, we went and we modified gamma in order to make sure that the system is stable again. So gamma here, which is the speed of the integrator, is your speed of adaptation. You remember when we started with gamma equal to 0.01, we were not able to converge in terms of parameters, and then the system is always chasing the change of parameter and the control. When we put it equal to 2, we were able to immediately converge in terms of value with very small peak in terms of dynamic of the theta, but we were able to have a better control and better learning, right? You remember this? Yes? Where is my head? Okay. So basically there is, this one controls the speed of adaptation. But also by changing the input, I found out this one can also stabilize the system. So I will make it lower. Making it lower means that I'm making it slower in terms of adaptation. So there is always a compromise between what we call robustness and the speed of adaptation. So we have to compromise always between how the system is fast to adapt versus stability. And this is something that we are going to face almost all the time when we do adapt. There is always a compromise between fast adaptation and robustness. Today we are going to go one step further. We are going to go for first order system. So this is my system here, a first order system. We have dy dt is equal to minus a times y plus b times u, and the dy n dt equal to minus am yn plus bm u c of t. Now the thing that I would like to bring your attention to is the fact that last time when I gave you the example, I started with the transfer function, right? I immediately start with transfer function. Can you please turn off your mobile?
This input that we give u equal to theta 1 uc minus.
I will come to that.
Oh,
but what's your question?
we're going to design or we make an assumption about it?
Park your question until we arrive there, but I will arrive to it and I will give you the chance. So this time I'm starting from differential equation. This is the state space for you, right? It's the first order, but the state space system. So this is my model. This is my reference model, And then I came here and I did again the structure of the controller. So remember these steps that we did last time? We said first we start with the system, the reference model, and then after that we assume the structure of the controller. Now for this system we have two parameters, A and B. Right? In the previous example that I did with the feed forward, there is only one parameter, K, right? Which is the parameter or the amplification that happens in steady state. In this one we have two parameters. So since I have two parameters, I had to have at least 2 degrees of freedom in order to satisfy these two parameters. So my controller cannot only be one parameter. Okay, it has to be more than one parameter. Everybody is okay with this? This controller can be decomposed on two parts, a feed-forward part and a feedback part. Right? So for example, I can say that I can add and subtract. So if you put here U is equal to theta 1 times UC minus theta 2 times Y. I can put this equal to theta 1 times UC minus theta 2 times UC plus theta 2 times UC minus theta 2 times Y. And then from here I can find this is equal to theta 1 minus theta 2 multiplied by UC plus theta 2 multiplied by UC minus 1. Right? So my controller has a feed forward part. This is coming from the reference. So I have the reference UC. It's multiplied by theta 2 minus theta 1. It comes like this. And then we have here the controller. This is Y. And then this will be multiplied by theta 2 and brought here.
Oh, makes sense.
Right? So I decompose my system in a feed forward part and a feedback. Everybody's okay with this? So, but in this case, when you look at it, you see only two parameters. But this is what it means.
How it's called. And A, M, and B, it's supposed that we know that because
This is
it's
your
the reference.
model.
Yes.
So your reference model now you are putting it in dynamic mode. Everybody's okay with this? So from here I took my controller, I replace it in the differential equations. And from the differential equations now I have dy dt is equal to minus a plus b theta 2 times y plus b theta 1 multiplied by uc. Theta 1, theta 2 are my parameters. A and B are the system. But you can see here there is one parameter that appears in the numerator, that will appear in the numerator, and there is one parameter that will appear in the denominator, in the characteristic equation. And this is why I put two parameters, right? Two flexibility basically.
The number of parameters depend on the structure of the equation.
It depends on the structure.
Differential equation.
It depends on differential equations. Depends on what I would like to have also.
So
Here,
for example, if you have the second order system, I have, for example, 3 or more parameters. More
yeah,
than two.
if we have more parameters, then we need to have more equations.
Okay.
So for example, if I have second order system, means that the system has friction or damping. So I need in my controller to be able to modify the damping.
Okay.
So I need to have another derivative, for example. If I would like to have a steady state error, it means that I need to add an extra equation for time. Theta t or u prime is equal to 1, right, the time domain. And then I will have to have a third parameter that will take care of this system. So I'll have a PID controller. Yes.
Sorry, can you go back to the how to get the feed forward and feedback terms?
I just took the controller. U equal theta 1 UC minus theta 2 times 1. Then I added and subtracted theta 2 times UC. So this and this is 0, but I'm not doing anything. I just took this term together. So this is theta 2 times UC minus 1.
Sorry, sir.
Yep.
Okay, so since we've been given the initial system in terms of a differential equation, in this case, does it make sense for us to convert it to a transfer function and then collapse or possibly collapse the number of coefficients we have here to a single one? Does it make sense that way?
Well, this is an excellent question. And this is the reason why I started with differential equations. I start with differential equations just to remind you that the MIT rule, the way we are using it right now, is input-output. It's not state space type of equation. If I was using Lyapunov, I need to start from here, right? But since I'm using MIT rule, since I use the MIT rule, then I need to go back and convert everything to input-output. Sounds good. Everybody understood what I did here? Everybody understood what I'm saying? Yes? No?
No, no.
No? So the MIT rule is an input-output. So we are looking to the feedback error, and we are saying the change of parameters is equal to minus gamma times E times the change of E with respect to theta, the parameter. It's an input-output. The equation that I gave you, the differential equation, is a state space model. So in order to go back and use the MIT rule, I need to convert it to input-output again. And to convert it to input-output, I need to use what's that? Is it clear now? So means that I need to bring myself back again to where we started last time. Last time we started with transfer function, input-output. So since I started with any other structure that is input, not input-output, I need to bring back the whole system to input-output. Is it clear? Does it answer your question?
Yes, yes.
All right. So now the next step is to compute the error. Because the rule is saying very simple, theta, derivative of theta with respect to time, which means literally the change of theta with respect to time, the way I'm going to update theta, I'm going to change theta, is equal to minus gamma times the error times the derivative of the error with respect to the parameter. So I need to compute the error. And the error is the difference between y and yn. So this is y, and this is yn. We have the same input, and I need to look to the difference between the two. The parameters that I have are theta 1 and theta 2. The unknowns are A and B. So the change of error with respect to two parameters. So I have a gradient of two parameters. So the change of the error with respect to theta 1, if I take the derivative with respect to theta 1 here, I will have B over
Plus this, please,
P
plus
plus
R.
A plus B theta 2. The use of P, we have talked about it last time,
Yes.
huh?
To come to time domain.
Because we are combining time and
And frequency.
Laplace. The derivative of E with respect to theta 2 appears in the denominator. So derivative with respect to theta 2 is B with a minus, so minus B. The whole thing denominator is equal to square, and then we have B theta 1 multiplied by minus B here. You are okay with this?
Yes.
طيب. Right now, if I look to B theta 1 over only one denominator times UC, this is the one, the function that we are getting, which is 1. Yeah. So basically what we are trying to do now is trying to convert this change of parameters, derivative of E with respect to theta 1, derivative of E with respect to theta 2, to some signals that we are measuring. Not the differential equation. Like exactly the same thing that we did last time. So let's go one step further. So in the derivative of E with respect to time here, we have B over P plus A B theta 2 times UC. Right? And this is this transfer function I don't have, because I don't know B, I don't know A. Here I don't know B, I don't know A, and the other side. So this change of parameter of theta 1 and theta 2 depends on A and B, and therefore my controller, which is theta 1 UC minus theta 2 UC, which is the integral of the derivative of E minus gamma times E times derivative of E with respect to time, is not feasible. Right? Cannot be realized. Why it cannot be realized?
Because we don't have A and B.
Because we don't have A and B. And now we need to make some mathematical manipulations. Okay? Mathematical manipulations, we are going to assume that our system, this represents the system in closed loop. E plus A plus B theta 2. We are going to assume that this equation, although we don't know B, but it's very close to what we desire. And what we desire is P plus A. Right? So I'm going to come here and say, let me assume P plus A plus B times theta 2 is almost P multiplied by P plus
plus A, yeah.
So this becomes derivative of E with respect to theta 1 is equal to B divided by P plus A multiplied by UC. And then derivative of E with respect to theta 1 is equal to almost minus B divided by P plus A multiplied by 1. Up to now everything is clear, huh? This is just an approximation.
The second one you mean theta 2, right?
So
The derivative of theta 2.
theta 2. Alright, now the change of parameters is equal to derivative of theta with respect to time, which is equal to minus gamma derivative of E of theta with respect to E. This is the MRAC rule. So I will start one by one. I will take derivative of theta 1 with respect to time is equal to minus gamma prime multiplied by B divided by P plus A multiplied by UC multiplied by E. And my question for you, why I called it gamma prime here?
Just highlights them.
Because why we called it gamma prime last time?
Just like
It's
Just do a differentiation.
Because we are going to add some constant later. So we said, okay, let's make it gamma prime, and then we will come back to it and make it gamma prime. Everybody's okay? All right. So this is what it is. This constant is this B. I don't know B. I know AM is coming from my system, but B is not known.
Okay.
So I'm going to take B and include it in
gamma.
gamma prime.
Absorb it.
Absorb it in gamma prime. All right. So if I add B and I absorb it in gamma prime, I will be end up with 1 in the numerator here. 1 over P plus A. Right? Now, this dy dt, if I put only 1 over P plus A multiplied by UC, multiplied by gamma prime, this is like a filtered signal, but the steady state error of this filtered signal will be not 0. Right? So I'll have something like this. Gamma prime multiplied by B out, and then I will have here 1 over P plus AM applied to UC. In steady state, the gain of the system is 1 over A. Everybody's okay? So basically what I'm saying, when I said it's 1 over A, it means that in steady state, this gamma prime times B will be multiplied by UC divided by AM. And I don't want this. I want to be UC. So I'm going to come here and we are going to add AM and divide here by AM.
Yes, makes sense.
Alright? Makes sense? So this term divided by AM, B over AM, this is just a constant. B could be anything, like last time, K divided by K0. So I'll absorb it in gamma prime, and I will say this is equivalent to minus gamma times AM over P plus AM times UC, the whole thing multiplied by the area. And now this becomes like UC filtered. Remember the filtered signal that we did last time? So this becomes like UC filtered. So I take UC and I filter it through a filter that is function of the characteristic equation that is desired by the system. I go to the next equation. We have the derivative of theta with respect to time is equal to minus gamma prime times minus B divided by P plus AM multiplied by Y multiplied by E. I do exactly the same thing. I take this B out. I take AM in numerator and denominator. And this becomes also a filter, which is the same one as the one that I'm using here. And the system can be equal to gamma times AM over P plus AM multiplied by Y multiplied by E. So if I would like to summarize, it will be what? First of all, we start with our system, whatever is the system. Right? It could be differential equations. If it's differential equation, I need to assume the structure of the model, compute the system in closed loop, convert the system back to input-output, define the error value, and then after that, look to the derivative of the error with respect to the parameters. In most cases, the derivative with respect to the parameters of theta will generate for you an unfeasible controller because it's function of the unknown parameters. So you need to do some approximation, right? And in these approximation, you refine them such that at the end of the day, the filter that you are going to put will not introduce any changes on your parameter or your system. So gain equal to 1. Right? If we are using second order system, not first order, then we are going to have here second order system. We are going to change the numerator again, and then we will have UC divided by second order system, which is our known system. يلا يا أحمد. امسك لي شوي. Everybody is okay with this?
Yes.
Any question about what I did? So remember, what I need now is to integrate this. To get theta 1, to get theta 2, plug them in the controller and get what I want.
Because if we have second order, so we need theta 3 here or just
If we have second order, we need to also play with the damping, so we need to have another parameter. Another parameter that multiplies the derivative. So we will have theta 1, theta 1 u minus theta 2 y minus theta 3 y prime.
y1.
Okay, so you have to add the derivative of y there.
So is this
Now, just 1 second. If we think with this, if we think this way, if we think that we have higher orders, then this theta 1 and theta 2 could be polynomials with different derivatives, right? That's it. So we go back to the
Original.
general form of RST. Yes, do you have a question?
no, my question was on the instead of using y prime, can we use the input or must we always use the derivative of the output?
Repeat this again.
I mean, when setting the controller
Yeah.
and we're introducing new parameters due to the increase in the order of the system, you mentioned that we will introduce y prime. So can we integrate the input instead of the output?
So we'll have theta 1 plus
UC.
the integral of the UC
No, derivative.
Derivative
of UC.
of UC.
If you make derivative of UC, we'll have derivative in the numerator,
Oh.
not in the denominator.
So you're not increasing the
You agree with me or not?
The order of the system itself is not increasing in terms of the number of
All the system increases in terms of size, and this is not an issue, right? So basically what we are saying is this. We have a second derivative of y with respect to time. طبعا you have to divide it. This one, if you would like to write it in state space, is equal to minus a1 times y minus a2 multiplied by y prime. This is your characteristic equation. Plus b multiplied by u. Everybody is okay with this? So if I put u equal to theta 1 times uc minus theta 2 multiplied by y minus theta 3 multiplied by y prime, I will have this controller here. It will be equal to minus a1 times y minus a2 multiplied by y prime minus b theta 2 times y minus b theta 3 multiplied by y prime. صح? And then we have UC, صح? Can have UC is here, plus theta 1 UC.
plus b theta.
And this is your second order system. So basically what you are getting is this, minus a1 plus b theta 2 minus
No, minus
Y.
minus.
There's y.
Why that one?
multiplied by y
Why?
minus
H.
a2 minus
One
b theta
okay.
plus b theta 3 y prime plus b theta 1
UC.
UC.
Okay.
So you have here theta 3, they will help you to change the damping. Right? So you have the flexibility to change the damping. And you have here flexibility to change the elasticity of the system. Right? So you change the damping and the elasticity. And there's this one, it will allow you to change the feed formula. If I come here and I add plus theta 4 multiplied by UC prime. UC prime will appear here, plus B theta 4 UC prime, which will be a 0 in the numerator. Right, so this is your denominator here will be S squared plus A1 plus B theta 2 times S plus A2 plus B theta 3, the whole thing, B theta 3 here, S, and here there is no S. And then this multiplied by 1 is equal to B theta 1 plus B theta 4 times S, the whole thing multiplied by UC. So you will have a 0 in the numerator. Would you like to have 0 in the numerator? If there is an stable power that you would like to cancel, it will be okay, otherwise it's not good. Sometimes we have to. What I did make sense?
Yes.
This one, please. I'll deal with it.
It's hot here, huh? Yes. Yeah, and if I was not standing, I would be sleeping there. Any question about what I did?
So this is a trial and error method, or
It's-
based on the assumption that we made.
Ahsan, it's a trial and error issue. It depends on the structure that you assume for your controller. If I assume, for example, only theta 1 you see minus theta 2 times y, I will find myself this term is A2 plus B. B is known, A2 is known, so I will not be able to change the settling time of the system. I will not be able to do this. You know, settling time is controlled by zeta omega n, the pole and closed doors, right? So this zeta omega n, zeta and omega n, zeta is here. If I don't have theta 3, I will not be able to change zeta. So if somebody gives me some time domain that are different from this zeta omega n, which is equal to A2 plus B, I will not be able to satisfy. The controller will not be satisfying the requirement. Right? So let's see how we do it. We do it in MATLAB. And what I did up to now, everything is clear? Right. So it's always exactly the same steps. Which step that you are going to start with before? Huh? So this is what the first controller. Now we need to write the controllers in order to be able to compare. So we are saying the first one, derivative of theta 1 with respect to time is equal to minus gamma multiplied by am over p plus am times uc. The whole thing multiplied by e. And then the second one, we have derivative of theta 2 with respect to time is equal to plus, which is am, the gamma multiplied by am divided by p plus am times uc. The whole thing multiplied, and the time is y, sorry. The whole thing multiplied by. One thing that I would like to bring to your attention, this value of gamma does not have to be the same. I could have different rate of conversions. Could be gamma 1, gamma 2.
So like it's a vector.
It's just a coefficient. Right? I decide about this value of coefficient. So I can change it the way I want. As I told you last time, there are some papers who use fuzzy logic, genetic algorithms, whatever it is, in order to generate these gammas.
Sorry. So like the fact that for the two parameters now, we have one that reflects the negative and one that doesn't.
Yes.
So that means the behavior of both parameters would be different, would be opposite of each other in terms of the change in.
Does it make sense for you?
So
Does it make sense?
does it make sense?
Does it make sense for you that this one has to be opposite to this?
I mean, with respect to the parameter that are changing with that they are attached to, kind of.
Because they're opposite in the equation.
They are opposite in the equation.
Yeah.
Their effect is opposite in the equation. So if I go back to the equation here, the equation of the error,
Yeah.
and I look to the error, if I increase theta 2, I will decrease the value. I will decrease the value of the error. So if I increase theta 2, the error will decrease.
So it's positive.
Sorry.
So it's positive.
If I decrease theta 2, the error will increase. So they have different signs, one opposite the other. However, theta 1, which is in the numerator, if I increase the value of theta 1, the error will increase. And if I decrease it, the
So
error
theta
will
2 need to be bigger than theta 1. Theta 2 need always to be more than theta 1 in the theta.
I'm not saying
Increasing, decreasing.
it can be anything.
They are opposite.
But what I'm saying is that the rate of change or the update of theta 1, the effect of theta 1, is the opposite.
Okay.
So this is why one is minus, the other one is plus. Alright, so if we look to this equations right now, that's one here. For example, if we take theta 1, what I need from theta 1 is the error, and it's UC. So I take UC, this is UC here, right? You see UC? And I put UC through the filter, which is AM over S plus AM, which is this one. And then I multiply the filter here by Y. This is the value of Y, by the error, sorry. This is the difference between YM and Y. Right? And this will generate for me the derivative of theta 1 with respect to time. This derivative. Then I push it through the integrator, and then the integrator I will have a gain, gamma, right, that I will change. This is an integrator. And this will generate for me theta 1 here. And theta 1 will multiply UC based on my controller. Everybody is okay with this?
Yes.
Now if I look to theta 2 is defined as Y filtered, so I have to go to Y, this is Y. I push Y through the filter, this is the filter. The output of this will have to multiply the error, so derivative multiplied by the error,
Gamma.
right? And then after that, I need to multiply it by gamma and integrate it to get theta 2. Integrate to get theta 2 here. Sorry, here, this one. Then the gamma 2 will multiply y, and then it comes negative in the feedback here. So this is, for me, this is U. Everybody's okay with this? And the rest I will talk to you about it later. But this is the implementation of the algorithm. This is my reference model, and this is my system. The reference model is BM over AM. I will see what BM over AM is, and then B over A, they are given here. So we have a program that gives me the initial values. So this is the initial value. The AM is 2, BM is 2, but the value of A is 1 and B is 0.5. Right? And I'm using here theta 1 0 is equal to BM over B, theta 2 0. These are the final values for my system. Right? From where I got the final values, if I go back here and I say what will make this system behave like this system, they are both equal. So I can equate the characteristic equation. So P and P are equal. A should be equal to A plus by B, theta 2 should be equal to AM. So from here I can say theta 2 has to be the ideal theta 2. Let me write it here. B theta 2 plus A has to be equal to AM. So this will imply that the the nice value of theta 2.
Steady state.
So this is the exact value of theta 2. If I have theta 2 equal to this
AM
value,
minus A.
theta 2 should be equal to AM minus A divided by B. Right? And the exact value of theta 1, I have B theta 1 should be equal to
BM.
BM. So B theta 1 should be equal to BM.
So
So the exact value of theta 1 should be
BM's over
BM over B. This is theta 1. So these are the exact values. These are, if you want, these are the theta 1 star, theta 2 star. This is the best I can get.
They should converge to these.
They should converge to these.
So it doesn't matter the first assumption, the assumption that we did that P plus A that plus B over theta 2 is equal to P plus AM.
It's
It
the
doesn't
same.
matter the value of AM as
Doesn't-
long as it's desired.
Exactly.
Okay.
As long as it's desired. Everybody, yes?
So, sir, just a little bit digressing from this, initially you mentioned that we imposed on, I think in the next slide.
Next slide.
Yes, sir. So the first line there where we impose the structure,
Yeah.
we say it's approximately equal to P plus AM.
Yeah.
So that basically means that when our system also changes, then this structure would basically follow that.
We don't care. We made the assumption, خلاص fixed. It's now it's B over AM. It could be different. Approximately means many things. Huh?
Yeah.
So it could be approximately 10 to the power 6, or it could be approximately equal to 200. So if it's 200, then we will have a transient until it becomes 10 to the power minus 6.
But does it make sense that if we go back to the former slide,
Yeah.
I mean the first expression here is just equating the denominator of the model we assumed and the model that we want.
No, I'm saying if I would like to have perfect model following, the closed loop transfer function. This one, we did it to the RS3s, huh? The closed loop transfer function, this one, has to be equal to the desired closed loop transfer function. This is perfect model following. So I did it. And that's it. I said, if there is perfect model following, theta 1 will be closer to BM over B, and theta 2 will be equal to AM minus A.
Why not fix it?
We don't know A and B.
That's another idea of MRAC.
That's the whole idea of the course. Alright? Yeah, did I answer your question now?
Yes.
You don't seem to be convinced. What is wrong? What is not clear?
No, I think the part I'm still trying to understand is if we've assumed the structure and we have the actual system here, and then in the next slide we are approximating the two expressions to be equal to each other.
I'm approximating them in my design.
In my design, exactly.
Yeah.
So can I make it as a rule of thumb that whenever I want to make the design, I approximate the denominator of the system I have?
What will be your other suggestion? I have a physical controller. This controller cannot be realized.
Yes.
I don't have the ABMD.
So how should I go? Cannot be realized. I cannot do it. I have two options. I have to go and estimate B and A, and we go back to
Recursive.
this square. Like we don't want to do this. We said now we would like to do it without
But it's
Identification.
fine.
direct.
or make assumptions. Even if the assumptions require that in the operating procedure there should be a modification in the way we operate. For example, when we take off with the aircraft, before putting the autopilot, it's all in manual. When we start the engine, before making the engine in autopilot, it's all in manual. So I bring it to a certain stage, and then I switch the controller. It could be this. This is what it will mean in real life. In real life, based on this assumption, it means that you have to bring the two systems closer to each other, to what you want, and then switch the controller off. Otherwise, you cannot switch it. But if I switch it from the beginning, there may be a transient. If the transient is safe, I'm okay with it. I can go with it. If the transient is not safe, then I have to have it manual. Did I answer the question now?
Yes.
Clear?
Yes.
All right. So we go back to this. So we are ready to run? Okay, let's run it and see what we have. Right, so based on this, I am comparing UC, the reference, to YM and to Y, and I'm putting them all here. Everybody's okay with this?
Yes.
So remember, the AM and BM, I took them in my simulation, both 2, 2. And a real system has A equal to 1, B equal to 0.1. So there is a difference between parameters. What is needed is 2, 2, behavior of 2, 2. The behavior of 2, 2 is the blue one. It's a first order system. The input you see is the staircase. The red one that you see here, or the brown one, it's your
Output.
your output of the system.
The
you have
blue is
to-
the desired.
It's not, first of all, it's not first order system. It's behavior like a second order.
It's conversion.
But the more you go, the more you converge. But it's a second order dynamic.
Yeah.
Everybody is okay with this? So for me, it's like the system is working, correct? The more we go, the more I'm refining. I'm refining the parameters of the system. And this has to reflect in A and B.
Yeah.
So because if I had the perfect A and B, it will be one over the other from the beginning, approximately. There should be certain, because this is second order dynamic. Yeah? So what we need to see, we need to see a transient change of A and B. At the end of the day, they will converge to the true value. Everybody agrees with this? So this is the curve that I have here.
So the values of thetas.
Sorry?
The values of theta.
The values of what?
Theta.
Values of theta 1 and theta 2, yes. So these are the values of theta 1 and theta 2. I start with the values of theta 1, theta 2 around here. This is the initial value of the integrator. And then they will start changing. And then they change, they change, they change, they change, they change. And they are converging where?
To 2, 2.
One
These two
point.
values. Star, star.
Yes, no, I am.
So you are going to converge in AM star here and BM star here. Theta 1 and theta 2. Alright?
Why we get this fall down like this?
Because of the staircase. Every time you go, it jumps to the airbags and then
I
it
get it.
changes and it comes back. And then it brings it back and then it goes again and again. We call this the learning curve. Learning curve.
Learning curve.
So the parameters, this is the learning curve of the parameters that you have until you reach the parameter that you want. Does it make sense for you? Now, ideally, we are going to converge to theta star and theta 2 star. But in real life, we may converge to another point. Right? Because here we are considering everything is nice. There's no disturbance, no noise, nothing. But if I add noise, or I add a disturbance, the system has, the controller has to absorb this difference. So you are going to converge to another value of theta 1 and theta 2. But you will see a learning curve like this. Right? So normally this in identification is very common. We see the identification, especially when we have more than one parameter in closed loop system, we are going to have a system like this. We are in closed loop here in this case. So the system is updating over this kind of shape until it converges to the last parameter.
Okay, how can we validate this if our parameters are correct?
How can we validate?
The curve of 4.
What I care about is
Output.
output. I care about two things, in fact. I care because this is input output control, and I put specifications. So the barometer, the scale that will tell me how good I'm doing is E, the error. which is the difference between the system and the reference model. If this error is within the specification I want, the requirement I want, 10 to the power minus 6, minus 3, minus 1, this is good enough. But theta 1 and theta 2 will affect the controller. So I need to make sure that theta 1 and theta 2 will not go nuts.
I see.
They have to give me a feasible controller. So I need to go back and check the control value, control level. I need to check if theta 1 and theta 2 stays finite. Because I may have, in simulation, a perfect model following if I take theta 2 equal to infinity, for example. But the system is not feasible. Cannot do it. Does it make sense?
Yes.
So two things then to verify. I'm mentioning these points because we are going to come back to them later. Right? It's all linked together. For me, in adaptive control, I need to make sure that the index function, which is E, the error, is according to what I want, specification that I want. So I'm minimizing the error. And the parameter that I'm estimating or identifying or using in the controller are finite, not infinite. Finite, and the control is reasonable, control level. Otherwise, I need to reduce. Now I'm using here the same value of gamma, but I could use different values of gamma. And these rates that you are going to see here, the slope in the middle, would depend on the ratio of gamma 1 and gamma 2.
If we increase in the time simulation.
If you increase in time simulation, you are going to converge better. So we can try.
Did you choose gamma with tuning or
Sorry?
did you choose gamma with tuning or with something like GA? Or?
No. Gamma just throw any value of gamma. But there's no GA, no TA, nothing. Alright? So we increase the value of time domain to 200. We can see what is going on here in the value of okay. So it's converging, and the more you go, the more it converges. So I think if I put this, there you see?
Looks like spider.
Now it's narrowing. If you continue, it will converge to one point and it stays there. It will not move. Now, but this behavior also, I told you this is the error changing, etc. changing, but don't forget that this is a nonlinear system.
So maybe
Right? You are multiplying U times C, U filtered multiplied by E, U filtered Y filtered multiplied by E. So the behavior is completely nonlinear. So this is why you see this kind of spiral. Now a quick question before I continue. Why I put parentheses there? AM divided P times P plus AM times
Because that's
UC.
the filter part.
Because the filter part. As I said, the filter is applied to a signal. It's applied to UC. It's applied to Y. If you take the filter, you apply it to E, and then you apply this to UC, it will get different answers.
Mathematically, is it not correct?
Mathematically,
It's the same equation.
mathematically, no, it's not correct. Because this is an operator. It's not a multiplication. It's an operator. Operator to U and C. What I said here makes sense?
Can you repeat those?
We have here P AM over P times AM times UC, or applied to UC. This is an operator applied to UC. I cannot take this UC out and put here E inside. If I do this, I will get different results.
We're not getting filters.
Right? This is U filtered, Y filtered. That's what we did in direct method. Right? Sometimes we have a second order here, but we will opt for first order, even if it's second order. We go for first order because first order is a low pass filter. So it will remove for you the frequencies that you don't like.
Low.
So you will basically sacrifice the fact that you are closer to the real system for the benefit of reducing the noise that you have in the system. Make sense? Now if we take this and we increase gamma, what will happen?
We learn faster theory.
Normally we said gamma here, I'm using gamma equal to 1. And gamma controls for you the rate of learning, right?
Yes.
So if I use gamma equal to something, then I'm trying to reach a faster adaptation. Which means that I may risk to have less robustness. So there is always a compromise between adaptation and
Robust learning.
robustness. So if I take, for example, here 5, these are
You need to do it also.
You can run it here directly.
Run it there, like from screen.
from simulate. What is it?
From the scope.
Please run it
That's wrong.
directly.
Let's see this first. Let's see how it works. See? 5 is better now than
We have oscillation in the beginning.
at the beginning oscillation. It's fine, but you see here, I gained something, huh? So if I continue, what will happen? If I continue increasing gamma, because you may be tempted to increase gamma.
It will be
So
unstable.
you are going to lose this performance. So there is a good value of gamma.
Up to
Over this value, you are going to lose the performance. But the speed of adaptation allows you to gain very quickly the perfect model for it. So if I continue increasing, at a certain time, what will happen?
unstable.
Unstable.
It's done with
250.
So if I go back to
Yes.
too much, huh?
I was expecting 50.
You can see also theta 1.
That's too much. Use 100.
69. So for this particular system, it may work for this value. Huh?
Because it's a first order. maybe.
First order system. And because the value of the input that we are putting here, the amplitude is equal to
1.
1. If you change the input, it may not work as usual.
Try it.
So if I take 10, for example, here,
It went crazy.
this one went nuts. I don't know where it went.
Exactly.
But the rest after that it came back. This is maybe a transient in the parameters that did not fit exactly the appropriate model.
But this is also.
But you see here, I just changed the input over my best behavior. I took my best behavior with theta equal to 10, the gamma equal to 10, and I changed the input and I got this behavior. So if it was a real system, everybody would be dead if it's a computer. So no need to continue the signal. And this is because of the transient of the parameters that we are trying to do. Everybody is okay? So there is kind of thinking of how to select gamma and what's the impact of changing the value of the input. You agree with me on this?
What if we play with frequency?
Sorry?
If we play with frequency, for example, calculate natural frequency for the system,
Yeah.
and we play with gamma in this value.
It will be loop shaping, basically in frequency domain. The problem is the fact that the system is nonlinear, so I cannot even go to frequency domain. Alright, in order for me to see how I'm going to select gamma, because this is one of the questions that we put at the beginning, huh? We said, how can we select gamma? The way we are going to do it is by just looking to the feed forward, because more than the feed forward, it's almost impossible. Without happening. Right? So I'm going to go back to feed forward and I'm going to say y is equal to k times gp applied to u, ym is equal to k0 gp applied to uc, u equal to theta times uc, the other is 1 minus ym, and the derivative with respect to t, we have found it last time, equal to minus gamma ym multiplied by e.
Okay.
So if I look to the equation of the derivative with respect to theta here, I can replace E by Y minus Ym, and then replace Y by K times GP times U, which is KGP multiplied by theta UC minus Ym. So what I will have now, I will have a differential equation in theta, derivative of theta plus gamma Ym multiplied by KGP applied to U multiplied by UC is equal to gamma times Ym squared. This is your differential equation for theta. And now how can we analyze it? This is the question. This is the VP, but we will call it later.
So,
Can we take Laplace transform?
again,
Can we take Laplace transform with this equation?
we have if you
We have P.
This is differential equations, huh?
Yeah.
Can we take the Laplace transform?
What is P?
Can you?
no because
Because of GP.
because
Yes.
You cannot take Laplace transform. This is GP applied to U times UC. This is a compound signal that you don't know. And believe me, there is a paper 2025 who took Laplace transform with this. I have no idea how they did it, but it was accepted and published in IEEE Access. But this is completely wrong. Right? So how we are going to analyze it? Our objective is to do what? How to find the
Two men of gamma.
gamma, so the optimal value gamma. So we are going to start making assumptions.